Okay, now let's look at multiple force member. Okay, now we've just looked at two force members, simplest case. Now very easy. Now, what if a member is subject to 3, 4, or 5 or more forces? Now what happens to the internal forces? Well, let's look at this example. This structure right here. This structure consists of a lot of members. This little straight member AD, okay, and then it's connected to this other link right here, this other rigid body CF, and then there's this other piece BE, okay, attached to it this way, and they're all pin connected, okay. And this AD member is attached to the ground, and also there's a cable, a little rope pulling from this D, okay, to the ground, joint G. And also at this end, we have a little weight that's hanging from this point F. Okay, slightly more complicated. Now this whole thing is in equilibrium. It's not moving. Okay, so static condition. Now, I'd like you to find what's going on at this red cross right here, inside of this AD member. Okay, right here, inside. So, in other words, I'd like you to find the internal forces right here in this position. Okay. Let's look at the free body diagram of AD member. Right? Since this point, okay, this point of interest is part of this AD member. So let's just draw it. So free body diagram of AD. Well, what you do is you isolate AD out of this entire connection. Right? So free it up, just draw AD, and then draw all the forces acting on AD. Okay, so you shouldn't have any trouble drawing that. Okay, well, let's look at what's AD subject to, right? So let's just, at this point A, well, we have reaction forces from the ground, right? This is a support. So, and since this is attached to the ground, right? So you have a two-dimensional constraint, right? So this constraint will resist, okay, this member AD, right, from moving, okay, in either horizontal or vertical direction, okay. So this resistance, okay, I'm going to draw like this way, okay. So I'm going to call it FA Y component, FA X component, right? So these two are the reaction forces from the ground. Let's say what else? Well, we have this B right here, okay? This point B is part of this BE member, right? So at this point B, there will be a reaction force, okay, coming from this BE. So I'm going to draw it right here. Okay, so that's B. But what's the direction of that force, that reaction force? Well, recognize that the BE member is a two-force member. And being a two-force member means that there has to be a force coming out of each end of this BE member. And they have to be directed along the BE direction. Okay? Which means that this force, the reaction force from this BE member, okay, on this AD member at this point, and this is point B right here, the force is exactly oriented along this BE direction. Okay? So I'm going to draw it like this way. Now direction I don't know exactly, so whether it points down or point up. Okay? But if you don't know it, just assume it. And call it FB. Okay, what else? I can just call it FBE. How about that? Right? Just to be consistent with my force convention naming. Okay? Just to signify that this force is pointing along the BE direction. Okay, what else? I have this C right here, somewhere here. Okay. Now this pin C, naturally we have reaction force or reaction forces, right? Now, how many forces are at C? Okay, is it just like this B, this FBE right here? Simple as that? Well, you can look at the CF member now. Now, CF member is not a two-force member. You have this force right here at C, you have this other force at E, and you have this other force F. So CF is subject to three forces. Okay? So the direction, the exact direction of this force FC, you don't quite know just yet. Okay? So we could actually alternatively draw two components, F, CF, X component, and F, CF, Y component. Okay, let's draw this component, X and Y component. Okay, so the magnitude, I don't know. Okay, but we do know that there are two components. Okay, of the reaction force coming from this member CF, acting at this point C. Okay. Next, I have, well, the last point. Okay, this D right here at the top. Right? I have this rope and it's pulling from it. So this direction I know. Right? So I'm going to just call it T for tension. Okay. And you do know that it's pulling. Right? So it's going down that way. So that's it. So this is the free body diagram for member AD. Okay, so 1, 2, 3, 4, 5, 6 forces. It's a 6-force member. Okay, now I'm interested in looking at the internal force. Well, somewhere between C and D, like here. Okay. So I'm going to do a cut plane, cut through C and D. Okay, I call this cut plane J. Okay. So what's going on at this position? Okay, inside this member, okay, along cut plane J. So just like what we did for the two-force member before, now I have cut through this cut plane J. Okay. Which means that now I get two sections, section AJ and section JD. Okay? Which one to analyze first? Well, take your pick. I like to start with the simpler one. Okay? JD, the smaller piece, simpler. Let's start with that. So let's look at the free body diagram of section JD. Okay, let's see what it looks like. So, draw JD. And then draw all the forces acting on this little section JD. Okay, so let's call this J right here now, right? Alright, so you do know right away that at D we have this tension force coming down this way. Okay, that's easy. Now, what else? Since this is a free body diagram for JD section, right? All these other guys don't appear here at all now. Okay? Now what else do we have? Well, there's nothing between J and D. Okay? But instead, what we have here, something at J. Okay, now J, okay, is a cut plane, right? So we cut through this member, okay, AD. Right? So there has to be something going on here at J so that this section JD can be in equilibrium. Okay? Which means that there has to be something so that this tension force T is cancelled out. Okay? Just so that in the end, this piece, this little section JD, is in equilibrium. Hey, that's nothing new. Okay? Equilibrium, well, just write down the equilibrium conditions. And you do know that we have three conditions. Sum of forces x equals 0, sum of forces y equals 0, and since this is a rigid body, you have sum of moment equals 0. Moment about any point. Moment about J or D or any point, doesn't matter. Okay? So some moment equals 0. So knowing this, right, these three equations must be satisfied in order for this piece, this little section, to be in equilibrium. There has to be, therefore, two forces at J. Let's go to F, J, Y. How about that? F, J, X component. Okay? So these two guys will counter this T, this tension force. Okay? Just so that this piece would not have any translation. Okay? It would not move to the right or left, or up or down. Okay? But what about rotation? Since this is a rigid body, this tension T would tend to create a rotation, right? So there has to be something else that resists this rotational effect. That's where this comes in. Right? Some moment has to be 0. So if I have a moment about J, okay, so this tension T would tend to create, what is it? A counterclockwise moment about J. So we have to have a counter moment, right? To counter the moment created by this tension T, which is exactly this. I'm called M. Okay? And that's it. These three guys, Fjx, Fjy, and M, are the internal forces at this J right here. Okay? Internal to this AD member. Okay? However, when we look at this JD section, these three guys now have become external. External to JD. Okay? But they're internal to AD. Okay? That's why they don't appear in this AD free body diagram, but instead they appear here. Okay? So these three guys are the internal, okay, internal forces and moment to this AD member. Next thing is just figure out the magnitude of each. That's all. Okay? Now, these three have special names to it. Okay? This Fjx, this is going this way, going sideways, or perpendicular to the direction of this JD or AD direction. Okay? We call it shear force. And the textbook calls it V. Okay, V for shear force. This Fjy, since it's axial, okay, axial along the axial direction of AD, okay, called axial force. Sometimes also referred to as normal force. Okay, textbook calls it N for normal force. This moment M, okay, It's actually a couple moment. Okay, you can look at it as a couple moment, right?